हेलो एवरीवन, वंस अगेन वेलकम टू आवर चैनल बीट द नीट। और आज मैं हूँ आप लोगों के साथ में फिज़िक्स ऑडियो बुक सेमीकंडक्टर का थर्ड पार्ट लेकर के। इसके पहले के दो पार्ट के मैंने लिंक आप लोगों के साथ में डिस्क्रिप्शन में शेयर कर दिए हैं, तो जिन लोगों ने अभी तक उनको नहीं सुना है वो वहाँ से जा कर के उनको सुन सकते हैं। उसके बाद में आप यहाँ पर कंटिन्यू कर सकते हैं। बच्चों, ये ऑडियो बुक्स आप लोगों को कैसी लग रही है मुझे कमेंट सेक्शन में ज़रूर बताइएगा। अपने कोई सजेशंस हो तो वो भी आप ज़रूर शेयर करिएगा ताकि मैं इसे और अच्छे से इम्प्रूव कर सकूं। और इसे अपने दोस्तों के साथ में ज़रूर शेयर करना और लाइक करना मत भूलना। तो चलिए स्टार्ट करते हैं। नंबर 2, लाइट emitting diode. It is a heavily doped PN junction which under forward bias emits spontaneous radiation. The diode is encapsulated with a transparent cover so that emitted light can come out. When the diode is forward biased, electrons are sent from N to P where they are minority carriers, and holes are sent from P to N where they are minority carriers. At the junction boundary, the concentration of minority carriers increases compared to the equilibrium concentration, that is when there is no bias. Thus, at the junction boundary on either side of the junction, excess minority carriers are there which recombine with majority carriers near the junction. On recombination, the energy is released in the form of photons. Photons with energy equal to or slightly less than the band gap are emitted. When the forward current of the diode is small, the intensity of light emitted is small. As the forward current increases, intensity of light increases and reaches a maximum. Further increase in the forward current results in decrease of light intensity. LEDs are biased such that the light emitting efficiency is maximum. The VI characteristics of LED is similar to that of the SI junction diode, but the threshold voltage are much higher and slightly different for each color. The reverse breakdown voltage of LEDs are very low, typically around 5 volts, so care should be taken that high reverse voltages do not appear across them. LEDs that can emit red, yellow, orange, green and blue light are commercially available. The semiconductor used for fabrication of visible LEDs must at least have a band gap of 1.8 electron volt. A spectral range of visible light is from about 0.4 micrometer to 0.7 micrometer, that is from about 3 electron volt to 1.8 electron volt. The compound semiconductor gallium arsenide phosphide is used for making LEDs of different colors. Is used for red LED, that was the GaAs 0.6p.4, and its Eg is approximately 1.9 electron volt, that is used for red LED, and GaAs, that's Eg is approximately 1.4 electron volt, is used for making infrared LED. These LEDs find extensive use in remote control, burglar alarm systems, optical communication, etc. Extensive research is being done for developing white LEDs which can replace incandescent lamps. LEDs have the following advantages over conventional incandescent low power lamps. Number 1, low operational voltage and less power. Number 2, fast action and no warm-up time required. Number 3, the bandwidth of emitted light is 100 angstrom to 500 angstroms, or in other words, it is nearly but not exactly monochromatic. Number 4, long life and rigidness. And number 5, fast on-off switching capability. Number 3, solar cell. A solar cell is basically a PN junction which generates EMF when solar radiation falls on the PN junction. It works on the same principal photovoltaic effect as the photodiode, except that no external bias is applied and the junction area is kept much larger for solar radiation to be incident because we are interested in more power. A simple PN junction solar cell is shown in figure 14.24. Here you can see a PSI safer about 300 micrometer is taken, over which a thin layer approximately 0.3 micrometer of NSI is grown on one side of diffusion process. The other side of PSI is coated with a metal back contact. On the top of NSI layer, metal finger electrode or metallic grid is deposited. This acts as a front contact. The metallic grid occupies only a very small fraction of the cell area, that is less than 15%, so that light can be incident on the cell from the top. The generation of EMF by a solar cell when light falls on it is due to the following three basic processes: generation, separation, and collection. Number 1, generation of EH pairs due to light with HV greater than EG close to the junction. Number 2, separation of electrons and holes due to electric field of the depletion region. Electrons are swept to N side and holes to P side. Number 3, the electrons reaching the N side are collected by the front contact and holes reaching P side are collected by the back contact. Thus P side becomes positive and N side becomes negative, giving rise to photovoltage. When an external load is connected as shown in the figure 14.25, a photocurrent IL flows through the load. A typical IV characteristics of a solar cell is shown in the figure 14.25b. Note that IV characteristics of solar cell is drawn in the fourth quadrant of coordinate axis. This is because a solar cell does not draw current but supplies the same to the load. Semiconductors with the band gap close to 1.5 electron volt are ideal materials for solar cell fabrication. Solar cells are made with semiconductors like Si, EG is 1.1 electron volt, GaAs, EG is 1.43 electron volt, CdTe, EG is equals to 1.4 electron volt, and CuI and Se2, the EG value is 1.04 electron volt, etc. The important criteria for the selection of a material for solar cell fabrication are: number 1, band gap, that is approximately 1 to 1.8 electron volt. Number 2, high optical absorption, that is approximately 10 to the power 4 per centimeter. Number 3, electrical conductivity. Number 4, availability of the raw material, and the 5th is cost. Note that sunlight is not always required for a solar cell. Any light with photon energy is greater than the band gap will do. Solar cells are used to power electronic devices in satellites and in space vehicles, and also as power supply to some calculators. Production of a low-cost photovoltaic cells for large-scale solar energy is a topic for research. Here you can see the examples. 14.9, Digital electronics and logic gates. In electronic circuits like amplifiers, oscillators introduced to you in earlier sections, the signal, current or voltage has been in the form of continuous time varying voltage or current. Such signals are called continuous or analog signals. A typical analog signal is shown in figure 14.27. Figure 15.27 shows a pulse waveform in which only discrete values of voltages are possible. It is convenient to use binary numbers to represent such signals. A binary number has only two digits, 0 and 1. In digital electronics, we use only these two levels of voltage as shown in figure 14.27. Such signals are called digital signals. In digital circuits, only two values represented by 0 or 1 of the input and output voltage are permissible. This section is intended to provide the first step in our understanding of digital electronics. We shall restrict our study to some basic building blocks of digital electronics called logic gates, which process the digital signals in a specific manner. Logic gates are used in calculators, digital watches, computers, robots, industrial control systems, and in telecommunications. A light switch in your house can be used as an example of digital circuit. The light is either on or off depending on the switch position. When the light is on, the output value is 1. When the light is off, the output value is 0. The inputs are the position of the light switch. The switch is placed either in the on or off position to activate the light. Here you can see figure 14.27, analog signal and digital signals. We will study it. 14.9.1, logic gates. A gate is a digital circuit that follows certain logical relationship between the input and output voltages. Therefore, they are generally known as logic gates. Gates because they control the flow of information. The 5 common logic gates used are NOT, AND, OR, NAND, NOR. Each logic gate is indicated by a symbol and its function is defined by a truth table that shows all the possible input logic levels combination with their respective output logic levels. Truth tables help understand the behavior of logic gates. These logic gates can be realized using semiconductor devices. Number 1, NOT gate. This is the most basic gate with one input and one output. It produces one output if the input is 0 and vice versa. That is, it produces an inverted version of the input at its output. This is why it is also known as an inverter. The commonly used symbol together with the truth table for this gate is given in figure 14.28. Number 2, OR gate. An OR gate has two or more inputs with one output. The logic symbol and truth table are shown in figure 14.29. The output Y is 1 when either input A or input B or both are 1. So 1 as that is if any of the input is high, the output is high. Apart from carrying out the above mathematical logic operation, this gate can be used for modifying the pulse waveform as explained in the following example. Here you can see the example. Number 3, AND gate. An AND gate has two or more inputs and one output. The output Y of AND gate is 1 only when input A and input B are both 1. The logic symbol and truth table for this gate are given in figure 14.31. Here you can see that. Number 4, NAND gate. This is an AND gate followed by a NOT gate. If inputs A and B are both 1, the output Y is not 1. The gate gets its name from this NOT and behavior. Figure 14.33 shows the symbol and truth table of NAND gate. NAND gates are also called universal gates since by using these gates you can realize other basic gates like OR, and NOT. Number 5, NOR gate. It has two or more inputs and one output. A NOT operation applied after OR gates gives a NOT OR gate or simply NOR gate. Its output Y is 1 only when both inputs A and B are 0. That is, neither one input nor the other is 1. The symbol and the truth table for NOR gate is given in 14.35. Here you can see the logic symbol, truth table for NOR gate. NOR gates are considered as universal gates because you can obtain all the gates like AND or NOT by using only NOR gates. Faster and smaller, the future of computer technology. The integrated chip IC is at the heart of all computer system. In fact, ICs are found in almost all electrical devices like cars, televisions, CD players, cell phones, etc. The miniaturization that made the modern personal computer possible could never have happened without the IC. ICs are electronic devices that contain many transistors, resistors, capacitors, connecting wires, all in one package. You must have heard of the Microprocessor. Microprocessor is an IC that processes all information in computer like keeping track of what keys are pressed, running programs, games, etc. The IC was first invented by Jack Kilke at Texas Instruments in 1958 and he was awarded Nobel Prize for this in 2000. ICs are produced on a piece of semiconductor crystal or chip by a process called photolithography. Thus, the entire information technology industry hinges on semiconductors. Over the years, the complexity of ICs has increased while the size of its feature continued to shrink. In the past 5 decades, a dramatic miniaturization in computer technology has made modern-day computers faster and smaller. In the 1970s, Gordon Murray, co-founder of Intel, pointed out that the memory capacity of a chip approximately doubled every 1.5 years. This is popularly known as Murray's law. The number of transistors per chip has risen exponentially and each year computers are becoming more powerful yet cheaper than the year before. It is intimated from current trends that the computers available in 2020 will operate at 40 gigahertz, that is a 40,000 megahertz, and would be much smaller, more efficient and less expensive than present day computers. The explosive growth in the semiconductor industry and computer technology is best expressed by a famous quote from Gordon Murray. If the auto industry advanced as rapidly as the semiconductor industry, a Rolls-Royce would get 500,000 miles per gallon and it would be cheaper to throw it away than to park it. Summary. Number 1. Semiconductors are the basic materials used in the present solid-state electronic devices like diode, transistors, ICs, etc. Number 2. Lattice structure and the atomic structure of constituent elements decide whether a particular material will be insulator, metal or semiconductor. Number 3. Metals have low resistivity 10 to the power minus 2 to 10 to the power minus 8 ohm meter. Insulators have very high resistivity that is greater than 10 to the power 8 ohm per meter, while semiconductors have intermediate values of resistivity. Number 4th, semiconductors are elemental Si and Ge as well as compound GaS, CdS, etc. Number 5th, pure semiconductors are called intrinsic semiconductors. The presence of charge carriers, electrons and holes is an intrinsic property of the material, and these are obtained as a result of thermal excitation. The number of electrons Ne is equal to the number of holes Nh in intrinsic conductors. Holes are essentially electron vacancies with an effective positive charge. Number 6. The number of charge carriers can be changed by doping of suitable impurity in pure semiconductors. Such semiconductors are known as extrinsic semiconductors. These are of two types, N-type and P-type. 7th, in N-type semiconductors, Ne is more greater than Nh, while in P-type semiconductors, it is vice versa. Number 8, N-type semiconducting Si or Ge is obtained by doping with pentavalent atoms, that is donors like As, Sb, P, etc., while P-type Si or Ge can be obtained by doping with the trivalent atom, that is acceptors like B, Al, In, etc. Number 9, NeNH is equals to Ni square in all cases. Further, the material possesses an overall charge neutrality. Number 10, there are two distinct bands of energies called valence band and conduction band in which the electrons in a material lie. Valence band energies are low as compared to conduction band energies. All energy levels in the valence band are filled, while energy levels in the conduction band may be fully empty or partially filled. The electrons in the conduction band are free to move in a solid and are responsible for the conductivity. The extent of conductivity depends upon the energy gap between the top of valence band and the bottom of the conduction band EC. The electrons from valence band can be excited by heat, light or electrical energy to the conduction band and thus produce a change in the current flowing in a semiconductor. Number 11th, for insulators, Eg is greater than 3 electron volt. For semiconductors, Eg is 0.2 electron volt to 3 electron volt, while for metals, Eg is approximately 0. 12. PN junction is the key to all semiconductor devices. When such a junction is made, a depletion layer is formed consisting of immobile iron cores devoid of their electrons or holes. This is responsible for a junction potential barrier. 13th, by changing the external applied voltage, junction barriers can be changed. In forward bias, N side is connected to negative terminal of the battery and P side is connected to the positive. The barrier is decreased while the barrier increases in reverse bias. Hence, forward bias current is more while it is very small in a PN junction diode. 14th, diodes can be used for rectifying an AC voltage. With the help of a capacitor or a suitable filter, a DC voltage can be obtained. 5th, there are some special purpose diodes. 16th, Zener diode is one such a special purpose diode. In reverse bias, after a certain voltage, the current suddenly increases, that is breakdown voltage in a Zener diode. This property has been used to obtain voltage regulation. 17th, PN junctions have also been used to obtain many photonic or optoelectronic devices where one of the participating entity is photon. A. Photodiodes in which photon excitation results in a change of reverse saturation current which helps us to measure light intensity. B. Solar cells which convert photon energy into electricity. C. Light emitting diode and diode laser in which electron excitation by a bias voltage results in the generation of light. 18. There are some special circuits which handle the digital data consisting of 0 and 1 levels. This forms the object of digital electronics. 19th, the important digital circuits performing special logic operations are called logic gates. These are OR, AND, NOT, NAND and NOR gates. Now there are some points to ponder. The energy bands EC or EV in the semiconductors are space delocalized, which means that these are not located in any specific place inside the solid. The energies are the overall averages. When you see a picture in which EC or EV are drawn as straight lines, then they should be respectively taken simply as the bottom of conduction band energy levels and top of valence band energy levels. Number 2. elemental semiconductors SI or GE, the N-type or P-type semiconductors are obtained by introducing dopants as defects. In compound semiconductors, the change in relative stoichiometric ratio can also change the type of semiconductor. For example, in ideal GaAs, the ratio of Ga and As is 1:1, but in Ga-rich as As-rich GAS, it could be respectively of Ga 1.1, As 0.9 or Ga 0.9, As 1.1. In general, the presence of defects control the properties of semiconductors in many ways. Number third, in modern day circuit, many logical gates or circuits are integrated in one single chip. These are known as integrated circuits. Chapter done. I hope that this audiobook will help you a lot in your preparation. एंड आप लोग मुझे कमेंट सेक्शन में ज़रूर बताना कि आपको नेक्स्ट चैप्टर कौन सा चाहिए, और इसको लाइक और शेयर करना मत भूलना बच्चों. तब तक स्टे ट्यून विद मी. बाय बाय. टेक केयर एवरीवन. सी यू सून इन द नेक्स्ट वीडियो.